Hi everyone. I'm Jeshwanth Challagundla. I work as a senior machine learning software engineer at Google. Today, I want to talk about like Gen AI feature development, like what is involved in developing features on top of generative AI models, large language models, basically. Just a disclaimer: this is just what happens. This is not specific to Google. This is what happens across the industry. Um, so yeah, so let's start with the evolution of language models. Like what made it possible? What evolution in model architecture made it possible to have this high quality, like the great performance with the latest large language models. So I mean, roughly this is how the evolution of language models look like. So we started with simpler models like bag of words and word to vec. I'll explain them shortly. And then we then moved on to using recurrent neural network and LSTM architectures, which kind of digest the uh, text sequentially, and then we have transformers which can digest the information parallelly. So bag of words is, you can think of bag of words model as basically you have a huge piece of, let's say you are doing sentiment analysis on input text. So you have a bunch of input text and you want to do some classification on whether this is the sentiment, how does the sentiment look like. So what you do there is you take basically the input text and you have a vocabulary, and you basically take count the number of words in the input text, in the vocabulary, and that becomes your input vector. So that's bag of words model, and you use this input vector like shown here. Basically, here you see the counts of each words in the input text, and then that would be the input for some linear classifier, which would then classify it into um, classify the sentiment of the input text. So you can see the problem here is that we are not, there's no ordering, so it's just counting number of the words in the input text. So there's no ordering information, there's no semantic information, etc. So it's just basically there's a bunch of vocabulary, and you are counting how many, like how many words do you see in the input text. So and then we moved on to the word to vec model. So this word to vec model enabled to create embeddings for each of these words. Like embeddings is basically like say a vector of floating point numbers for each word, giving having like which has some, which basically encodes some meaning of that word. So the way they so these embeddings have basically somehow has the meaning of the word. So if you take an embedding of a king and then subtract the embedding of a man, word man, and then add embedding of word woman, you will get embeddings that is close to queen. So basically, the embeddings of each word is encapsulating the meaning of the word, semantics of the word, etc. So that gave us, like, now we can understand what each word mean, and these embeddings can be used again for each of the embeddings of each of the word can be concatenated together, and we can apply a classifier to again do sentiment analysis. Now the quality is much better because you understand the meaning of the word. You're not just counting the words, you are using this vector for each word that somehow encapsulates the meaning of the word. So you can see how the performance can be better with these models. And then we and then comes the recurrent neural networks. So this is where so the word recurrent here means basically the same network recurs again and again. So basically, here is a network that is basically attending to, I should not say attending, but that is basically digesting one particular token. You can think of token as a word in the input text. Basically, the network is digesting one word in the input text, and then it goes to starts digesting the next word and next word and next word. So it does this in a recurring manner. So that's where the name recurrent neural networks comes from. So the model digests the first word and then emits some hidden state that can be used when digesting the second word. and it goes on like that. So it starts digesting the second word, and then and consumes the hidden state that is emitted when digesting the previous word, and then and emits a new hidden state for digesting the next word. So and then it keeps going until it digests all the input, and for generating, at the last token it starts generating the output. So before that, all the output we can ignore until it digests all the tokens. It reaches the last token in the input, and then it starts generating the output token, and then the output token becomes a new input token, and it's in an autoregressive way we start generating. That's how the recurrent neural networks work. But the biggest problem here you can see is this information pathway, that you have to go through this bottleneck of information pathway. So whatever the previous recurrence emitted, whatever the hidden state the previous recurrence emitted, that's your input. So you can't see what's happening before that. So whatever the model decided to emit in the previous turn, the previous recurrent turn, that's the only thing the current recurrent turn can see. So you can see how the information can be lost. You can't remember things like what happened, like 4 words before. You don't know what happened, like things like that. So that was the reason why the quality was not very good. And then and then there was some advancement on this, like called LST, called long short term memory, where they made they kind of created a pathway for information, a free flow of information. And at every state you can add in some information, and like memorize some information, or remove some information, basically forget some information. So there's a free pathway. You can add in some information and forget some information. So this improved the quality to some extent, but still you can see it goes in a recurrent manner, visiting token after token. So after this comes the transformer model. So this is what enables all the LLMs, all the generative AI models, all the quality you see with the latest like GPTs, ChatGPT, etc. So this is the architecture. So like, but at the core of transformer is what we have is like the attention. What is shown here is the attention block. Uh, so we'll go over the attention very quickly. So attention is where, so here what happens is in attention, you have the input text, and then like for each token, I mean, let's say token is a word. For each word, we compute 3 vectors, query key value for each word. And then the query is like, now query is, we want to, so okay, we have a query for a particular word, and we want to take this query and multiply with all the keys in all the words we have in the input text. So in a way, the product of query and key will give us how much this particular word wants to attend to all the other words in the input text. Like this word feels more important to me, like this particular word. So once you do the dot product, like between query and key, query of this word and keys of all the words, then I basically get the attention score kind of, and then we normalize, and then we kind of get some probabilities you can think of, like how much I want to attend to different words in the input text. And then we take a weighted sum of all the values of the different words in the input text, and the weight is basically the attention. And that's how, and that would be the output of this word, output of the layer, output of the attention layer. So in a way, each word is kind of grabbing information from all the other words, uh, not like weighted by the attention score, like how much it cares about a particular word. It's weighted by that information is all aggregated together, and that would be the output of a layer. So output of this layer, and you'll have multiple layers. So in a way, you can see how the information is being shared and digested in every attention layer. And as you add more layers, you'll go to deeper and deeper levels of abstraction of what this particular word, or this particular embeddings is kind of understanding from other embeddings, and then it keeps going. So that this is what enables, so now you can see how a word can attend to any other word, and there's no bottleneck, information bottleneck. And this is what enabled all the quality gains, all the things we are seeing with the LLMs. So here, this is just um, Here you can see how each word can attend to other words, and the attention will have different scores. Like it doesn't attend them to them uniformly, but based on the attention score. Um, so yeah, that's about the model architecture. And now the transformer is what that attention layer is what enabled all the quality. Now looking into, now we have this architecture. Now how do we train a model? So so at the core of it, now when we start with a model, we have this all this quotation layers, everything initialized to random numbers. um, so the model just predicts something random. You give this input text and predict some random token. So we need to train the model to make it predict the right next token, high probable next token. So for that, usually it has three stages. So one is pre-training, where we just teach the model, train the model on a whole bunch of documents, internet, from the internet, code, everything. And the model kind of learns, like understands English, and then like basically builds knowledge on what on the information, like what comes after what. Basically, it's building knowledge on a broad spectrum. And then supervised fine tuning is where we fine tune the model to basically behave in the way we want. So now it is trained on documents, so the model will kind of behave like document generator. So if you give some document as input, it'll generate more of the document. So in fine tuning is when you teach the model to behave like an assistant, behave like in whatever way we want. Basically, for this input, you need to provide a response in this particular fashion. Like, and then the other thing is RLHF, which is basically reinforcement learning, which is like kind of a self improvement, um, and then which further boosts the quality of the model. So before training, the first step is, now these models cannot take the raw text as input, so we need to convert this into numbers. So this process is called tokenization. We basically take the input text, then we convert them into tokens. A token can be a word, a single character, a piece of word. It can be like group of words. So the way the tokens are decided is basically inefficient. So there are algorithms to determine tokens, and they are basically optimizing how can we have this vocabulary in English. How can we compress them in very less number of tokens? Like, but you can say, okay, if you use each character as a token, then you can, that's the best compression. But then if each character is a token, then this text would become in token. When we convert this text to tokens, each character becomes a token, and the length of tokens would be would be large, and that is not good for the model, because model can only see some context window, and it's problematic for the context window. So it's an optimization between decreasing the vocabulary size and also keeping it not too fine grained, because it'll affect the context window of the model. So that gives us the tokens, and each token is just basically a number, then maps to a number. So that's how you convert raw text to numbers, and this numbers is what is inputted to the model. Now I'll skip this, but yeah. Now, so for pre-training is basically we are teaching the model. You take any piece of text, like you take all the documents on the internet, uh, high quality, low quality, all those documents, and then you can weight them in different. Like you can give more weight for high quality documents and less for low quality documents. And now you have a document. You take a piece of string in that, piece of text in that, and and then you say, okay, we have all the character, all the tokens from all the first 100 tokens are my input. The 101 token is basically my target. So here you can see the yellow, all these tokens are basically my input token, and the model is trying to predict the one in the blue square. And the actual target is, I know the next word, I know the next token, so I know the target. The model is predicting something, and I'm training the model to make its prediction as close as possible to the target. So this is what is happening. So given this input text, model predicts the next token, and we want this token to be as close as possible to the actual token we see in the document. And after doing this for several iterations on trillions of documents, then we basically get a pre-trained model, which gained a bunch of knowledge and understands English and all that. Now, at this stage, as I said, the model doesn't know how to behave. What it knows is, you give me a document, I'm just filling the document, I'm generating more and more of the document, next token, and so on. So it's just a document generator at this point. Now, to make the model do what we want, like for the features we are developing, we need to fine tune the model with an instruction following data. Like, given this input, I'm asking you to do something, you need to do that, not just generate more of what I said. So this is how roughly a fine tuning data look like. So we have what we are asking. This is the user. This is what user is asking, and this is how you behave. Like, this is your response. We take like probably thousands of this data, and then we train the model. The model starts behaving that way. So now it becomes an assistant, useful assistant. So for your given user, given prompt, it's basically responding with an answer. So usually this pre-training step um, happens in months, maybe years. Now it's happening in months. So pre-training usually happens like 10 TB of text, and then like huge lot of GPUs, and then like whole bunch of money, and you have the pre-training model. So that's why you don't do it very frequently. But fine tuning would be on thousands of examples. So you'd kind of do it, iterate on this frequently for your feature. So you add more data, you see problematic areas, you add more data to fix that. So you do that. So basically, you kind of get some evaluation, and then you fix the losses in the evaluation with the more data, and then you keep doing this. And this cycle can be in days, weeks. So now you are improving model's quality and following instruction and responding in the way you want for your feature. And now next is RLHF. So RLHF is kind of interesting, where it's a kind of a self-improvement loop. It kind of helps to improve the quality even more than SFT in a self-improving manner. It doesn't need a lot of data. So basically, we start with bunch of prompts, just like user queries. No responses are no find like responses are curated. It's just prompts, and then we sample multiple responses from the model. Like, so, and then we have multiple responses, and then we score them. We need an RM model, someone to tell like which response is better. So we use something called reward model for this. I'll go over how we train reward model in the later slide. But there's some model telling which of this response is better for this prompt. And now we train the model saying, okay, now encourage the behavior of like a good response and discourage the behavior of a bad response. And you can see this, you can do it again and again, and then slowly drift the model performance towards giving desired responses. Like whatever RM model is encouraging to do, slowly the model tries to learn that and gives responses which are preferred by RM model. So now to train the reward model, so reward model should somehow able to tell which response is good. So for this, what we do is like you take the prompt, you sample multiple responses from the model, and you ask users like vendor like humans to basically pick which side is better, and they pick basically, okay, this side is better than the other. But usually comparison is comparing two sides is much easier than telling exactly like is this one side better or not. So they just compare two sides. Okay, this is better than the other one. So kind of like a elo score. So they're comparing responses and telling this is better than the other one. They keep doing that, and this is how we get so much reward data telling one response is better than the other. And then we train the reward model. The reward model will be trained with this data, and it learns how to tell differentiate between a good response versus bad response, or like a desired response versus undesired response for our feature. Now that's how we get the reward model, and the reward model will basically be used in the RLHF loop, telling the encouraging the responses that are good and discouraging the responses that are bad. So this RLHF will give us extra gains, and then we further boosted the quality. So the model is behaving even better now for our feature. Now, these models are very big. As I said, for fine tuning, I mean, it costs millions for pre training, and like around the same, like again, millions for fine tuning. So, so training a raw model, like fine tuning the whole model is kind of very expensive, and it takes a lot of money, time, etc. So an efficient way of fine tuning the model would be you take the base model, like whatever the pre trained model, fine tuned model, and then you add some additional weights to different layers, like all the query key value and all that. You add some additional parameters. And when you train this additional parameter. So in a way, you have this base model and you are learning some additional stuff with this added parameters. So this way you're so when you train, you're only training these additional parameters and you don't touch the pre-trained, like the base model. And these additional parameters are usually much smaller when compared to the whole all the parameters in the model, in the pre-trained model, in the main model. So it's very efficient to fine tune. um, yeah, but again, there are only few parameters you're training, so what you can learn from this is also limited, but this is good enough for most of the features to just, because we are only changing the behavior of the model, etc. We are not just pre-training the model, we're just fine tuning the model behavior to our particular feature. So this is good enough for the those use cases. Now I'll come to now we have this model trained and all that. Now, how do we give a user query or give instructions to the model? Like how to efficiently extract more performance by providing right instructions. So this is called prompting, like asking the model what to do is prompting. And now there are different techniques, like, so prompting, in a way, you can think of it as instructions that we write. So this is what the model sees, and we have user query and the model response. So instructions, like we are asking it to, like saying you're a large language model, you need to respond to user in a nice way and all this, follow these instructions. Here are some examples of how to do that, whatever. So these are system instructions. There are different techniques for this prompting to improve the model performance. So there's like zero shot, few shot. So zero shot is basically we don't say anything. We just ask question and see whatever model gives. That's zero shot. So zero, basically we're not giving any hints, any examples, etc. So few shot, we give some examples. So here is an example input, here is an example output. There are like 3 4 examples. Now here is the question, give me the answer. Chain of thought is more interesting, where we're asking the model to think and think in steps and then respond. So the model kind of have some thinking and like says, like, give some reasoning before it comes to the final answer. So this improves the quality by a lot. So a simple thing like, so this is what, when we ask the model to think step by step for a query like what is the percentage difference between India and China's population, the model cannot answer this directly. It needs to get the population of India, China. It needs to do some math. It needs to tell the answer. All this cannot be done, like model cannot just generate the answer for it directly. It has to go through the thinking. So it should start generating the thoughts and then getting the answers for each of this thought and then finally getting the answer. So this is what happens with chain of thought. You can think of this as like system one thinking and system two thinking. Without chain of thought, the model is just giving the answer. So usually this works for very simple queries. Even humans do this. So if you ask 2 plus 2, you immediately respond. But if you are given a like little complex math, then you'll start thinking slowly about it, breaking it down, probably do like 10 into 24 plus 7 into 24 in your mind. So this is the same thing that we are achieving with chain of thought. So for complex queries, you need the model to think. You need the model to use more tokens to think before generating the tokens of the answer directly. So just simple prompt like let's think step by step. You ask a question and just say let's think step by step, and the model, you will see better quality with this just small piece of text. So now this is how you prompt it. So this would give most of the things you need for the feature development on GenAI. Now we need, if you want to make the model more accurate, because models are trained or pre-trained once in a while, so their knowledge can be outdated. So to make the model more accurate, we can use retrieval augmented generation, which is nothing but for a given query, you can also give additional information to the model before it generates the answer. So you give query, also you can search the query and then get relevant documents and add that to the query and give it to the model. So the model basically knows the question. Okay, here is a question and here are some documents that I got from search. So that document will have some relevant and latest fresh information. So the model can basically digest it and then respond in a relevant with relevant information. So this would remove all the hallucination problem of and outdated knowledge problem of LLMs. The next interesting thing is tool use. This is very powerful. This is what is enabling making enabling all the agents, making the models even more powerful. So the models are able to use calculators, or able to write Python code, run Python code, even interact with the computer, browser, etc. So all this is possible by tool use. Um, so tool can be so model can use tools like basically by generating special tokens, which then can be taken, and then a tool will can be triggered, and then the response is fed back to the model. For example, the model can decide, okay, I want to search for population of India for this query, like difference between India and China's population. The model decides, okay, let me search for this. We're not like get like in the previous slide, I'm saying we search for it and give it the information, but here the model is deciding to use a tool when it wants. So it says, okay, I want to search for something like population of India. Okay, we go on this piece of code that is basically but there's a tool that takes this query and then gives a response. So the response is, okay, India's population is whatever from Wikipedia. And then it search for China's population. Okay, here is the China's population. Now the model wants to do some math, so it can trigger a calculator tool. So it's a calculator tool, and there's a calculation, and this is the response. And then model has everything to respond, and now it says, okay, the percentage difference is so and so. So now you see how powerful the tools can be. So the model can do a lot of things with this tool. So this tool, one of the tool can be execute code, like Python code. So here is my Python code, execute this and give me the response. So it can write Python code, execute the code, and then get the response back. It can do the same for, I mean, if it wants to interact with your browser, it probably can again do like write piece of code and then execute it and interact with some internal browser it has and things like that. So this enables like this is how you build all the features using this agents tools. You can think of this tool as an agent also. If this tool is not a piece of code, and but if it's a piece of if it's a model, then it's an agent. So you are basically invoking another agent to do some work for you, and then you are getting the answer back from the agent. So this is how you're interacting with agents, and all the agents like, and then improve the like give you the desired output for your complicated query. So apart from this, there are other things like for improving efficiency, like caching. Um, like you don't need like with caching, you don't need to recompute all the query key values again and again, so you can cache them for the same piece of text. And then safety, like you want to make sure the model response is safe and all that, so you need to put train the model to respond in a safe way, or put some filters to filter out unsafe content if needed. And monitoring, you need to monitor how your model is performing, the quality, thumbs up, thumbs down, and all this. These are some other things involved in your when you're developing a feature in GenAI.